6D is titled Statistical Inference. Statistical inference is the process of making a conclusion about a population from results for a sample. This is important because most statistical studies intend to learn something about an entire population. Since it isn't possible to survey or measure an entire population, scientists often must use a sample. The process for statistical inference often starts with a question, sometimes called a hypothesis. This question is usually about a population, such as the entire U.S. population or maybe all Arkansans. Following this well-developed hypothesis, then the researcher carefully designs and completes a study using that sample set. Following the study, the researcher must analyze the results and infer the implications for the population. We will discuss statistical significance. In a statistical study, we want to be very cautious when assuming that there is a significant influence by a variable. So we begin our study by assuming equality. This is occasionally called the null hypothesis. In this hypothesis, we start by assuming that there is no possible influence by a particular variable. As an example, suppose that I wanted to compare the test scores from an in-person class to a remote learning class. When I begin this study, my null hypothesis is that there would be no difference between the test scores for the two groups. After completing the experiment that is well developed and thorough, if the results of the study based on the sample indicate that there is a substantial difference between the means of the two groups, the in-person group and the remote learning group, only when there is a substantial difference, which would be extremely rare under the situation where they were equivalent, only in this case should we reject the null hypothesis and select the alternative hypothesis. The alternative hypothesis being that there is a difference among the groups. Always assume equality unless the data suggests that that is extremely unlikely. The process for determining statistical significance often starts with a question, an idea. This question may just be about the difference in two groups, so the difference in the means of the two types of teaching methods. This leads to an experiment design. This theory may be the alternative theory. When completing this study, we must begin assuming that there is no difference. We then design and complete a thorough experiment. Based on the results of that experiment, we ask whether the results indicate a substantial difference that would not be likely if the means were equivalent. In the theoretical outcomes, there are two conclusions here. There may be no statistically significant difference in the two means, or the evidence may overwhelmingly suggest that there is a significant difference in the means. Next, we will discuss confidence intervals. The 95% confidence interval is found by adding and subtracting the margin of error from the sample portion. The purpose of this confidence interval is so that we can be 95% confident that the true population proportion lies within this interval. The margin of error is calculated using the formula we see here. N is the sample size, so 1 over the square root of n, or you can think of this as 100% over the square root of n, since margin of error is often given as a percentage. In this example, we will derive a confidence interval for the tossing of a fair two-sided coin. Suppose that we take a fair coin, we toss that coin 300 times or use a computer simulator to do so. We want to find the 95% confidence interval that represents the number of times we expect it to land on tails. And we would expect that 50% of those tosses would land on tails. However, if you start this experiment in real life, that's probably not the case. You might have a bit above or a bit below 50%. That percent above or below that 50% is called your margin of error. Our margin of error is given by 100% divided by the square root of our sample. Since we will complete 300 tosses, then n here is 300. We'll take 100% divided by the square root of that denominator. 100% over the square root of 300 is approximately 5.8%. This means that in a real-world experiment, by tossing a coin 300 times, we would expect 50% plus 5.8%, which gives us 55.8, down to 50 minus 5.8, so 44.2%. We would expect anywhere between these two numbers to represent the number of tosses we expect to land on tails. Notice that 44% of 300 tosses is 132.6, and 55.8% of 300 is 167.4. Therefore, when I begin tossing the coin 300 times, or using a simulator to do so, I won't be surprised if I have anywhere from 134 to 137 tosses of the coin which land on tails. This would be normal. These numbers lie within our confidence interval. If a value lies extremely outside of this interval, such as 200, suppose that 200 of the 300 tosses were to land on tails. This would make me suspicious that the coin was not fair.